Rotation interpolation is another method of trajectory planning. So this is typically done with a rotation matrix of the end effector. So that would be the orientation of it, and either Euler angles or roll pitch yaw. So the equation here that's given is a linear one. So the roll pitch yaw as functions of time would be the initial values times some fraction plus the final values times another fraction. So this never has a constant angular velocity, and it assumes start time of 0. Now, the one shown is linear. You can see that t is just by itself to the first power. But if you wanted a smoother response, you could use t squared or, t to the third power or so on. It makes the equation a lot more complicated. Now, this is only for starting position to an ending position, one continuous path. If you have midpoints on your path, you need one equation per path section. Start is the time that you finish the prior path, and end is the time that you finish this path section. So you would have to adjust the equations accordingly, where t is time, ts is start time, and te is end time for that particular section. Basically, you just offset all of the equations by the start time for that section. So let's go over to the whiteboard and do an example. If we're given a problem that a robot moves its end effector from a starting orientation of roll pitch yaw, 0, pi over 4, and pi over 2 radians, to an ending orientation of roll pitch yaw is pi over 3, pi, and 2 pi over 3 radians, over a period of 10 seconds, find a linear rotation interpolation trajectory and angles at t equals 5 seconds. So this is from start to an end, and they want a linear trajectory. So let's get the formula for that. All right, we've got the formula for it here. So basically, we just need to fill everything out with as much numbers as possible. So we'll have phi of t, theta of t, psi of t equals, and we put in the initial values, 0, pi over 4, pi over 2. That is multiplied by 1 minus t over the final time, which is 10, plus t over 10 times the ending values of pi over 3, pi, and 2 pi over 3 radians. All right, so this is the equation. So if we were to simulate this in Matlab as a function of time, we should get some lines. So let's check that. All right, so we can see the roll, pitch, and yaw given here in blue, red, and yellow respectively. And we see that the roll goes from 0 to pi over 3. The pitch goes from 0.78, which is pi over 4, to an ending value of pi, as expected. And then finally, 1.57, which is pi over 2. The yaw goes from that to 2.09, which is 2 pi over 3. So now we need to figure out what is the angle, or what are the angles at t equals 5 seconds. So here we just plug in 5 for t. So at t equals 5 seconds, then we'll get so those are the answers for roll, pitch, and yaw. Now let's go back to Matlab and visualize what these starting and ending positions would look like. So the black frame is the starting orientation and the blue frame is the ending orientation.